deep learning for the binary classification task, but now we will go for the multi-class classification task. And the focus here, you can see that various applications. So one such applications would be like multiple object land cover segmentation or multiple object land use land cover mapping from satellite images, right, or remote sensing images. In general, it is basically a multi-class semantic segmentation task. So one thing just to keep in mind always, segmentation is nothing. There is a classification we have done and the segmentation right now. Since segmentation, what will happen? Set of pixels belongs to a particular class or objects. That's called nothing, it's a semantic segmentation, right? Now when we say binary semantic segmentation, two classes. So entire image, there are two set of intensity values. If you have multi-class classification, then there will be a more than two objects in the image present, right? So that one particular set of pixels will be representing one class, other set of pixels representing the second class, and the next set of the pixel representing the next class, and so on like that. Depending on the data, depending on a task, what do you have? Like 3 class, 4 class in data set, or 4 class, 5 class. So these are the set of tasks which could be used as a multiple object extractions. Focus would be a land cover mapping or predicting the thematic map. This examples already you have seen, right, as a part of multiple object extraction, but it's a multi-class semantic segmentation where object of interest is only two, that a building and road. So here the line, red line represent that your networks. So this is ground truth, and corresponding the building part here you see, the printed model which already you have seen that. And this examples already you have seen as a example of multiple object extractions. Just quick, I think not seen that previously. You see that this example as a 4 class classification. This you have seen that the PPT were doing the example of land cover mapping, right, in the introduction part, okay. This 6 class classification, and apart from this, you can use, the previous was aerial data, right, that Google images and so on, right. Here is the satellite data, which is called Landsat, right, Aconus 2, right, Sentinel-2, right, like lot more the satellite data you can use. And here if you see there are 6 classes, here you see that 8 classes from the data set. So this is our paper, again was published in 2020, and this paper we did not use those days deep learning. We have used the meta-heuristic approach, right, and the traditional deep learning methods, right, and traditional machine learning like SVM classifier use that, okay. This was a hyperspectral data which you have seen already from the Professor Fabio as well, right. So University of Pavia, where Professor, who has created this data set?
Initially, for the understanding or demonstration, whenever we search for hyperspectral data, we find
So University of Pavia created by the boss of Professor Fabio, right, Paulo Gama. He only created that. Yes, he's actually that created the data set, right? And it's hyperspectral means University of Pavia is one such search, right? Such data will be used extensively, right? Apart from that, University of Pavia, right? There is called Indian Pines data is there, and some more data also as available. You can do as a land use land cover mapping or land cover classification, right? And apart from this, you can also do like as a mapping type, forest, different type of forest object segmentations, right, which you have not earlier seen. So you see that there are different input data, and then we have called here the 4 classes. So 4 classes is representing here like non-forest, coniferous forest, mixed forest, and deciduous forest. So different type of forest, right, classes are represented 1, 2, 3 here, different colors. and the A is as original image, B is your ground truth, and the C is predicted from the UNIT simple model, right? So you see that UNIT is most of the remote sensing research, UNIT model you will see a lot of applications, right? Whether forestry application, urban land cover mapping, or even this cloud segmentation, no? UNIT is a base, right, used for the mapping, right? But the research has gone beyond that, right? UNIT is not only that, people have come up with very lot more models as well, right, for remote sensing. This is again, very interesting as a multiple object land cover mapping from the SAR data. So here you see that there are three set of data basically, which comes from SAR data Hong Kong, Istanbul, and Washington. So these are the big images, SAR images of the regions, okay, of their particular country, and corresponding is the right side is the ground truth part, right? If you see, okay, there, and these are the classes already like mentioned in the ground truth, all classes. And here if you see there is called small patches and there is called large patches, right? So if you see here, this is a large patch area, right? And the one is small here, three small regions, right? So likewise, each images here also is there similarly, this also is there. So here you see that small patches, three different regions like 1, 2, 3, right? So these three regions used for doing land use land cover mapping, and then this is here corresponding three ground truth, and corresponding three they are predicted out by different models. And currently this method like CCNR, which was this paper, right, is 2023, very recent work, last 23, right now. So you can see this result is quite closer to the ground truth, right? That's part from the SAR data, right? So this is one like from the SAR data. Likewise, other examples you can see that here these three images, all things can be also explored that. So if you open this paper, right, just read that whenever you get time, and if you have some interest, right, you can explore more examples and more data set, what data is used, city, all things you can read the paper, right, get more information. So these are the source of data for when they're doing the multiple object segmentations, right? This you have seen that here. So these are the two popular data available, not two, even many are available, will come set. So these two are the basic data set called RS Learning Aerial Image Segmentation Map 2017 was used extensively, and then this came in 2020 from the Poland, and this paper was introduced. This having the very good data set, and in fact lab, not this lab, all right, I can share, if who is interested I can share that you can work on that, and also you can download and work on that, not a problem, okay. But since you started learning that in the beginning, you may not find you can work all the images on the Google, right, Colab or any. If you have good computing resources, then you can work on the entire data set, otherwise you need to work on the custom data set. Custom means take it 50% or 40% or 60% based on your computing resources available, okay. This is example of the data set, 4 classes, right, you can do. Divide patches of 412 cross 412 and label into 4 classes, water, building, woodland, and so on, right. This is the link, right, from where you can get the data set. Apart from this, you see deep globe building extraction data set also there, right. You can see that input data, and there are classes, right. Here classes, all the corresponding with ground truth represented, and this is a link, right, from where you can download. See, spatial resolution is 50 centimeter per pixel. That means very high resolution data, right. That was used for the deep learning application, training set, validation tests, all things are detailed. Data is not a problem in any field now. Problem is patience, time for developing the algorithms, right. First do that task, okay. Data is available. And then the 7 classes you have seen. Likewise, many data also available. So these are the models, right, which deep learning, advanced deep learning model, I start from the basic. See, you have seen this is a base model, start from learning from here. Don't do FC and all thing not needed, right? Your the first model should be a unit model only. First built right unit model, right? Implement for binary classification task or the multi-class classification task, okay? And then SegNet, all things you can do, and then DRNet, these three models, see, 2022. After this, we were able to publish 2022, then 2 papers in this task, and then 23 is the other paper which we designed, come up with this. So this model, right, unit model. So in the model, what are the concepts you need to understand? One is convolution, right? Okay. I hope everyone have idea convolutions. Raise your hand who are familiar of that convolutions. 1, 2, 3, 4, 5, 6. Majority people are knowing right now. Second is here called upsampling layer, right? So upsampling is that concept which are called interpolation method. You are aware of that, no? Those methods are the, I mean that kind of, manual feature in methods, right now. You, for a specific thing, you have to select which method will be good or bad, right now. If you want to do upsample. Instead of that, right, we can go to the like called transpose convolutions right now. So 2D transpose convolution is more better than the traditional upsampling method like interpolation methods, cubic, bilinear interpolation, cubic, all those things, right now. Instead of using those, use this advanced, because here you need not to select that. It will automatically learn from the, right, from the model itself, parameter itself. It's like no automatic changes will happen, like filter, all things will happen, right? So instead of using upsampling concept like bilinear or cubic interpolation methods, use transpose convolutions, okay? So, and this is the model. I think previous slides, can you go? I'll just quickly explain that transpose convolutions, then we'll come back here. This you minimize. Previous lecture. In the same folder is there. 1, tutorial 1. Okay, I'll go. Leave it. Okay, so this is convolution. I hope everyone is aware of that. Okay, right? Leave it. No, this let me open full screen. No, previous was better. Fine, leave it. Okay, so it's not moving. It's not moving. Achha, okay. No, it's okay. So this is how convolution happen. Like 3x3 kernel, right? And then take the start from here, and 3x3 do the element by element multiplications, right? And then you will get the 1 pixel value, nothing 1 feature values, okay? And then do the stride 1, same operation, right? And then you will get 1 feature values. So convolution is a linear operation, always keep in mind. Convolution is a linear operations, right? That's why after that we are using the ReLU activation immediately, so that we have to introduce a non-linearity, so that more better learning feature extraction will happen, right? But this has to, can you go forward? This should work, right? Because yes, fine. So you can see that happening, right? 2D convolutions, which you can see that. And this is how you computed already. I told you the formula, right? And size. This is your convolve feature map H3 and W3, and this is D2. D2 is nothing that how many kernel or the filter used for doing a convolution operation. If you use 10, right? So you will be end up to get the 10 feature map here, right? That will happen. If 5 filters, 5 feature map you will extracting, okay? So this is input image which is 4 cross 4, right? And this is your kernel. So what is the resultant will be 2 cross 2. Why? Use the same formula. This formula use it, right? You can get that. And here there is no padding happening. Convolution without zero padding, right? So that's why the size reduction is by 2, okay? Because 3 cross 3 kernel case, right? And this, how to do that? There are various methods of doing convolution operations, right? One such method is called matrix method, right? So in matrix method, first you need to create the convolution matrix, okay? So convolution matrix, right, can be created by rearranging the value of the kernel itself, right? So whatever the kernel bits are there, right, kernel values, right, 3 cross 3, from there only we can create a convolution matrix. So this is convolution, the kernel 1, 4, 1, 1, these are nothing, these are the bits, right, kernel bits. From this we will be creating a convolution matrix, right? How we'll do that? So first is create a 0 array of 1 comma 16, 1 row 16 columns. First you have to create by using np.zeros 1 comma 16, okay? So this is array will created that external mat this, right? Next step is replace values by the kernel, right? Each value or 0 we have to going to replace by this. How we'll do? For I in the range of wk, wk is the bit of the kernel, which is in our case is 3, right? And this value goes to 0, 1, right? 0, 1, 2 only, right? So this is extend matrix I comma h colon I comma h plus hk. Hk is the height of kernel, which is 3 here, right? I equal to k comma I. K of k in bracket I means I start from 0, 1 and 2. When say 0, this will be coming here, right? So entire matrix only what other things will be replace it? This side inside, right? You can just do that, right? I equal to 0, 0 into 4, right? H is a height of the input, right? H is a height of that input image, right? Which is a 4 in our case, right? And HK is the height of kernel, which is a 3 here. This is input 4 cross 4. This is kernel, which is 3 cross 3, right? Keep in mind. Okay? You keep on substituting this, the value, whatever this coming inside this matrix, going to replace it, right? Change that, okay? That will store here. So first case, I equal to 0, 1, 4, 1 will replace. Then I equal to 1, right? This second will go replace 1, 4, 3, right? Then I equal to 2, here 2 into 4, 8 colon, right? 8 plus 3, 11. So 8 colon, this 13, right? Positions. So here this is going to replace 1, 3, 3, 1. Clear? That makes sense? Next step. Once you created the previous, right? Next step is creating the convolution matrix. So convolution matrix after rearranging the kernel, which is 3 cross 3 into a 4 into 16 matrix. Why 4 into 16 matrix? Because this is decided by the data what we have. So here output size is 2 cross 2 means total 4 element. What input? 4 by 4. That means 16, right? So if also you know this part, so convolution matrix, if you know the output, right? Or if you know output, you know the input matrix, you can also find out what is the size of convolution matrix as a like box, right now. So this part we need to flatten it, input data we need to flatten it. Once you flatten, what happen? 1 into, I mean 16 into 1, right? We have to column matrix, right now, 16 column, right? So if that column vector is column matrix 16 into 1 and output is 2 cross 2, which is nothing, 4 into 1, right? 4 row column. So easily you can get, no, what will be the size of matrix, right? 4 into 16, right? Now, so we need to create a 4 into 16 matrix, right? That as here. So this is a first rows which already we created the previously here, right? And then this is called extend kernel, and this is 2 for loop use for I in the range of W underscore O. WO means output, width, which is our case is 2. HO means 2, which is in our case 2, right? Because why? Already we know that what is the output, the feature map size. And J, I 0 this, J in the range of HO, and extend matrix 1 NP dot roll extend matrix comma H into I into S plus J into S. So H is, I is your iteration and S is tied, which is will be 1 by default, okay? And then extend matrix equal to NP dot array extend kernel, right? So here you can see that, and this appending in the matrix what we created that kernel. So I again, if you look at that, I equal to 0, 4 cases. I equal to 0, right? K equal to 0, right? I equal to 0, K equal to 1. Third step, I equal to 1, K equal to 0, I equal to 1, K equal to 1. 4 cases. So just follow the 4 cases and put it over here, right? So just I'll tell you, case 2, case 0 no problem, case 0 case what happened? Same as will be input, right? Case 2, I equal to 0 and K equal to 1, right? So what happened here? Here just to see that here, I equal to 0, I and H, this is 4, 0, yes 1, and this is 1 into 1. That means 1 unit roll. Roll means this fellow will come into shift here, like rolling, right? Now, last fellow. Understand now? I equal to 0 and K equal to 1, right? Next step, I equal to 1, J equal to 0, right? So I equal to 1, here what will happen here? 4 into 1, right? I equal to 0, right? Completed row. I equal to 1 and then J equal to 0, right? So this 4, right? 4 into 1 into 1 plus 0, right? So that means 4 element going to shift, roll, right? So from here to 4 element, just shifting will happen, right? This part, 1, 2, 3, 4, these 4 fellows, okay? Clear? Fourth condition, I equal to 1, J equal to 1. Total how many shift roll will happen? 4 plus 1, 5, right? So 1, 2, 3, 4, 5, you see that. Clear? This is how this matrix is become, we create a 4 into 16, right? Clear? And then input need to be flattened. Once you flatten, we'll get 16 into 1, 16 rows, 1 column matrix. Next step is, this is matrix, convolution matrix, multiply with that column input vector, and then do that, you will get 4 into 1. 4 into 1, we have to reshape it. This is first row, second row, right? Reshape it, you will get this part. Clear? This is called matrix method doing convolutions. To do the transpose convolutions, very simple. Whatever the matrix you have calculated, already you know, already you have in hand. Same matrix, take the transpose and the convol feature map, convert into the column vector, do the element by element matrix, you will get the output of a transpose convolutions, right? Very fast. So this ReLU already you know, I hope not going to teach you this thing. This is need of upsampling. So from the smaller size, we have to create a high resolution images. And convolution is many to one mapping. Always remember, many to one mapping. Many to one mapping means 9 element we have seen is mapped into 1. Okay? Upsampling is a reverse, 1 to many mapping. In the sense that from one sample we have to create a 9 sample values, right? Non-feature values. Okay? Reverse. So this is a transpose 2D convolution with no padding instead of 2, you can see that. Okay. From the input we are creating this data. Okay. So these things you already know, like bilinear interpolation, right, bicubic interpolation methods as upsampling, but as I told you, these are the like handcrafted feature. For specific things you have to select manually, right. Instead of that, we can go for the transpose 2 convolutions, and it's very powerful. It learned from the network parameter itself only. Need not to do initialize and all things. Need not to depend on the what specific like interpolation methods we have to select that. Okay, because it is used created from the previous available the filters, right, whatever use convolutions and all things, right, and it is used mainly on the DC GIAN and the semantic segmentation model extensively. That's a 2D transpose convolutions, right, and it's also known as deconvolutions or fractional styled convolutions as well, right. So going back, as I told you, we have to do like already many to one mapping. Now we have to one to many mapping. We have to reverse, right. So like upsample. So from the 2 cross 2 matrix, right, we have seen that 4 cross 4 into 3 cross 3 resultant was 2 cross 2 convolved feature map. From that convolved feature map, we need to reverse get to 4 cross 4. That's only objective. Okay, that's called upsampling right now. So this is how from we have to do that, like reverse one to many mapping, right. From this corresponding we have to generate that. I'll come back straight forward. So what the thumb rule says that, like whatever the convolution matrix is there, just take the transpose of that. That's all. So this is a transpose. Previous was 4 into 16. Transpose of will be what? 16 into 4. So this is 16 rows 4 column, and then convolved feature map, which was 2 cross 2 matrix, right? Just flatten it. So this is a flatten. Do the matrix multiplications. Resultant is what? You'll get that 16 into 1 matrix. Reshape it. This is a 4 cross 4 matrix, right? Input was 4 cross 4, and then after upsampling we are getting also 4 cross 4, right? So size is not a problem. With this upsampling, what it does, why it require? Whenever do mapping land cover, right, we want the segmented map looks, you are able to see the object in that. If it is smaller, teeny, you can't see object. But if you have no larger resolution dimensions, you can see the object very clearly, all the things, right? This is one as example, right? As a simple things you can code, implement from the scratch and understand that, right now. So this is how here use, like we do like max pooling here you have see, and this is what we do the upsampling here. This is base, upsample, here copy crop, and then 2 times the same convolutions, then upsampling, then we need to copy and crop, make it same things, and then like this will go, and finally here 1-to-1 convolutions will be using at output layer for doing the binary segmentation. If you do multi-class, this will change, right? That makes sense? So what I wanted to explain you, transpose convolutions is very powerful, and transpose convolutions is nothing. Usually you can do from the convolutions if you have in your hand, right? Transpose of the convolution matrix, multiply with the convolved feature, flatten it, do the matrix multiplication, usually you can get that, right? Okay, so here that practical this practical implementation of single object, then we'll move for the multiple object as well here. So here these are the steps, but these steps are common for multiple object as well. Like this case building 2D CNN model for single object land cover mapping. Collect data set of the single object, maybe road, building, cloud, foreign, etc. from publicly available data set. Understanding and pre-processing of data is must. Step 2, creating 2D deep learning models using the software, right? Deep learning Keras framework or the TensorFlow or PyTorch. Then training of 2D unit model on the training samples. Then the testing of 2D unit model, right, on test samples. Performance evaluation of 2D unit model, right, various quality matrices. And then the testing of 2D unit model on the new samples, right? New samples means is not there in the data set. Like random you have captured from XYZ sources. Like for example, you have train from the Mangalore city, right? Or let's say Nagpur only, right? So maybe specific area you have been chosen. That's for train, you capture the big area, right? So some you have used training and some you testing, right? Apart from the Nagpur, whatever study area is data, some other region you have to choose and test on that, which was not there in study area while training the model. That's called new samples. If model works good, your model is very good. That's more generalization happen, right? So this is building data set here, Massachusetts. So if you see that resolution is 1 square meter, covering the area of 2.25 kilometer, and it originally having the 1500 cross 1000 pixel size, in the sense that the one image is a bigger size. From this size, they created the sample of patches of 512 cross 512, okay? And this is a data set, table form, you can get all the things right now. So Massachusetts building, training sample validation test, size was original this, Massachusetts road data this year, this already given that this Carto set 2E road data set we have created as an ITK, it's basically Indian geographical regions, Indian satellite, that's called Carto set 2E, ISRO satellites, right, which study covers the South India, Karnataka, that's Bhopal, North Indian regions, that's called Bhopal. So Bangalore, Bhopal, and third is called Imphal, Nagaland side, northeast side. So very different regions we have selected, and then the data set which we have created is called road of the 3 different variety of the, their landscape regions, right. So this data set we have created, paper is revision. I hope by next month you may see the paper, and data set also will be released for entire. That's enough, right? This is, I mean, it's good result. You may not get like for deployment applications. This indicates that yes, whenever you adding the data set, performance of deep learning is better than. So like it's like new data set, new benchmark for Indian communities, okay, which is very typical task right now. Anyone can use, but created something for others. So we have going to create, already created, but soon will be available for public right now. So this is a sample like building road, and this is called Indian road data set, right? So you can see that as this model already. So while implementing single object activation, right, four component already keep in mind, right? That should be a nonlinear activation function always used inside the neural network, inside the deep learning model, whatever you choose. Normally we are preferring the ReLU activations, right? Inside that, it could be even the variants of that, maybe ELU, SELU, PRELU, right? Lot of things are there, SELU, lot of variants of activations are there. Second is loss functions. So for single object case, you have to use the binary cross entropy as a loss function, ideally value 0, practically should be close to 0. And then optimizer, you can use SGD, you can use the ADAM also, it's up to you, right? Anyone output. Output layer using the sigmoid activation functions. All things are mathematically you can see here. ReLU, binary cross entropy minus k goes to c, tk log FSK. FSK is nothing the y hat predicted output, right? Which is nothing here, math expression like FSK equal to 1 by 1 plus e to the power minus sk, which is sigmoid activation function. And minus sign always indicates we will try to minimize the BC value, always, right? If it's plus, we want to maximize the value, right? But as here loss means always objective will be minimize the function value, right? And there is a reason math, right, why we have to do, right? Because since loss, so we always say we have to minimize rather than maximize. It's already proven, right? Maximization and minimization both are, max and minimum are the same point. If you are doing minimization, you are the same, your max and minimum point remains same. If you are maximizing also is same. So you can go for the minimizing rather than maximizing, right? Because your max and minima point are the same, okay? So these are the training of unit. You have to use anyone, you can use the models, and underfitting overfitting problem you may encounter. Try to know overcome these limitations by increasing that. So always use the batch normalization if you want to improve the training side. Avoid overfitting, regularization, dropout, early stopping, cross validation. These are the options. Avoid underfitting, get more training data, increase the model complexity if required, and parameter increase, training time, right? Cost, you have to minimize, you have to training time increase until the cost is going to minimize. And sometimes if data is in balance, you can make it the data set balance, right? If you are doing the image based classification, otherwise may not be necessary, right? So this part will, so where is that previous next switch PPT? Next, second one, right? No, second nahi tha. First part. Second open.
Multi objects, huh?
So now we can quickly take it further from there. So this model were there, right? Same model now. Same model can be used for single object, right? And can be used for multiple object, right? So now for the 2D, like multiple object extractions, steps remain same. Whatever I told for single object, same step continued for get the data, right? Collect the data of multiple objects from publicly available resources. Then you understand, do pre-processing. Here there is a lot of pre-processing. There is called one hot encoding and one hot decoding is must. That I'll teach you quickly. And then creating 2D unit model. Rest everything is same steps. Whatever I told for the single object, right? So this is a data set which called high resolution remote sensing data set. That's called land cover mapping, which is having 4 classes: water, building, wood and rest area. And these are the test samples corresponding to the ground truth. These are study area, as I told you, comes from the Poland. Rural areas of 216.27 kilometer, 39.5 kilometer with the 50 centimeter per resolutions and 176.76 square kilometer with the 25 centimeter per pixels, right? That means the resolution is 25 centimeter per pixel and 50 centimeter per pixel. It's a mix of resolutions, right? And training set consists of 400 images and corresponding ground truth tests and test samples are the 100 images. But when you start learning, don't use all the data set. You can just work on the custom data set, 400 training samples to 150 into test samples. That would be enough for in the beginning phase, right? Whenever you have a high-end computing resources, like you have a 16 GB GPU and then you have good memory, right? Then you can put all the data in one go only, right? Training that. So data pre-processing, right, is very important, as I told you, right? Especially for the multiple object land cover mapping case, right? So if you see that here, this is you see image, right? Right? But computer understand only the numbers, algorithm understand numbers, right? So this data image which having the 5 classes, 1 to 5, like person, purse, plant, sidewalk, and then your buildings as structures. These 5 classes, if you see right side, which we call as a semantic label, right? Each color representing the specific class with the color only, right? 1, 2, 3, 4, right? So 5 classes, 5 different colors are used. Clear? Okay. Input image this, but the semantic label will be this. This is nothing your ground truth in a semantic label form. But normally the ground truth, whatever we see, it's RGB image. Yes or no? Right? RGB also will be ground truth image. But that ground truth image, the algorithm will not accept. Algorithms will accept only that algorithm RGB image need to convert into semantic label. So that RGB ground to day image need to convert into this form. Okay, that's called pre-processing. That's called one hot encoding. Okay, so how will work it? So from the one hot encoding for the converting the RGB ground to data into a semantic label. So first we need to create the output channels. Depending on the number of classes, we need to create the output channel with the same size. Size will be remain same. So since there were 5 classes, so here you see there are 5 channels are created, right? So like here the purse and then person, purse, plants, sidewalk and building walk. So wherever is the object like person is there, that will be 1 with the red color. Rest every will be 0, right? Likewise for the purse, so location in the image where is a purse will be 1, rest will be 0. And then for the plants, where is the plants in the image? That will be only 1, rest will be 0. Here the height and width will be remain same. Whatever the height of the width is there will be remain same, will not change. Okay. Likewise the sidewalk. So sidewalk you can see the image here and here is there. Here is there sidewalks. So you see that here 1 and sometime here is there. Okay. 1, right? And then the buildings. So wherever is buildings, right? Building and structures will be marked as a, if you see here 5 classes, but as a output channels will be here like this, 1 will be marked, same colors, clear? So from, once we have created the output channels, from the output channels next step is we need to create a semantic label by using argmax. How many of you heard the argmax concept? Argmax, softmax, function? Softmax give a probability for the classes, okay? Softmax gives the probability for the classes, right? If you have suppose 10 classes, right? So if you use softmax give you the probability for all 10 classes. Then on top of that, to get which specific image belongs to which specific class, we need to use the argmax function. So argmax function, what it does, it will see that, right, which columns is having the highest probability. If like column number 2 is having highest probability, then it will say the input image belongs to the class 2, like that. Okay, so it's nothing, it's looking just finding the maximum probability, that's all, nothing else, okay. So from this is overlap of the semantic label on the input data. You can understand this example very clearly of the land cover data set. So 4 classes, right? And this is the image what you see. This is the portion of a ground truth, not entire. Ground is just for visualization point of view. So this data, we need to convert this. So first step is what? We have to create the 4 output channels with the these colors, right? And then we need to do the algorithm process, right? So this is one hot encoding method, which is you can see my DPPNet paper nicely explained, right? You can understand the later on. So this is set of codes, pseudo code for doing one hot encoding, right? So this one hot encoding methods, right? Time is less, I will not explain, go for much, right? So like color dictionary, then RGB one hot encoding methods. So here we will be giving the input image RGB color, ground truth and the color dictionary. Color dictionary nothing means, right, which particular color belongs to which particular objects, like 0 to like 4 classes. Here 4 classes, so color dictionary is a 4, right? Total number n will be 4 here, right? So n is a number of class in the data set. So here will be, in our case will be 4, right? And then do the complete procedures like shape calculated, then array created 0 shape with array number n channels, right now? And then find the color here like 1B, we have seen that, no? Getting this output channel here, right? And then we have to do the one hot encoded as a mask, we are generating that. So argmax of array, whatever we have created that earlier, right? This array here is storing that values. That will give you the one hot semantic label. In fact, your the deep learning model, whatever design for multiple object case, is also giving you the semantic label output. So to get to see the image predicted map, you do the reverse operation, one hot decoding. So means semantic label we need to convert into the RGB image. Okay. So for that we will using called one hot decoding of the procedures, right? So from means semantic label into the RGB reverse. So here the input for this will be what? Semantic label, right? What will the output? RGB image, right? So process very simple on what to RGB. So one hot data, color dictionary will be same, get the safe information which will be your maximum 3 plus 3, right, which will be giving you that safe values, and then RGB equal to 0 safe, you have to create that, and then again one loop, color dictionary, and do these operations. Finally that color dictionary converting into the 1 RGB data into key. So wherever is like there was 1, 2, 3, 4, right, get converted into the color corresponding. Assign the class and then finally get the RGB image, right. Okay, concept clear? Right, you can read paper, write more detail, right, not an issue. So this is coming to the implementation. So here activation and optimizer you can freeze. Whatever you use for the unit case, single object land cover segmentation, you can use the same things. Only need to change the loss function and the output layer, right. Since you are doing the multi-class semantic segmentation or multiple object land cover segmentation, so you have to use the this critical cross entropy loss, right. But in library this is called semantic loss, you have to use that semantic critical cross entropy loss, you have to select that basically for doing a for multi-class semantic segmentation task. I will show you later on, right, possible. So optimizer freezing, output layer always using the softmax activation. This is a formula for softmax. FSI equal to ESI divided by sum, J goes to C, ESG. C is a number of class. In our case, our data set is 4 classes, right. Okay. This training setup is remain same, right, nothing new. Coming to the performance models. So whether you have single object, multiple object, you need to compute the various quality matrices, which I think Professor Fabio already has given some thoughts like precision, accuracy, recall, all the things, right. I will not as much visually looks this aerial data, segmented output, and this is your ground truth label image, target image, okay. So this is for single object case, get a confusion matrix, and you can get the accuracy, precision, recall, F1 score, and IOU. Keep in mind, if you do image based any classification task, right, then intersection of union is not an important matrix. If you do a pixel based classification, then this is very important, intersection of union or Jaccard index, right. And rest all anyway precision, recall will be there, but classification case again you need to do some more matrix called, what Professor also told morning, kappa coefficient. Kappa coefficient is more balanced accuracy analysis than the that average accuracy whatever you see the model gives you, right. So precision, recall, F1 score is this need to know, right, very important. From this you can get the true positive rate, false positive rate, right, and then true negative rate and false negative rate, all things you can also compute as a additional matrix. Apart from that precision, recall, F1 score, accuracy, IOU, you can also see these other rates as well, right, as error analysis. So these are the mathematical, the formula to compute the all the true positive rate, right, not false negative rate, true negative rates, false positive rate, all things you can get it from the confusion matrix, right now. So these are the all values, already explored that, and this is Jaccard index. Jaccard index you can also compute from the confusion matrix. If you have, if you doesn't have, still you can use this formula other like this what say that union intersection of mod of intersection of segmented, right, versus the ground truth, and then the this is mod of the union values, okay, or you can use this formula, right. Okay, so here already the S is segmented output, G is your ground truth data, right. This is called Jaccard distance, can we use as a loss for the your single object segmentation task, right now. This is more on the intersection of union, IOU. You see that IOU, area of overlap, right, that's called intersection, and area of union of entire everything, two things, right, you can get the values. And this is how the example state how role of the IOU, right? Poor IOU, good IOU, excellent IOU, right? Which is normally used also for YOLO object detection task from like YOLO all kind of things task, right? You can also compute the F1 score or Dias coefficient. This is nothing, the F1 score is harmonic mean of the precision and recall, right? You can compute. This is formula from, you can compute 2TP divided by 2TP plus FP plus Fn, right? You can get the Dias score or the F1 score, right? And corresponding you can get the Dias loss. Dias loss equal to 1 minus the Dias coefficient, right? That can be used as a loss. Okay, so you can use for single object binary cross entropy loss, you can use Jacquard distance loss, as you can use the Dias loss, right? Now you can have options. And the maximum value is close to 1, right? Close to 1, right? Ideal value is 1, right? Ideal value 1, but ideal never will reach. Close to 1 if you get, that's very good, right? These thing, accuracy, right, formula, standard things you know. Apart from this called macro F1 score, and you can get, and then you can do macro and micro, right? So this is called average precision. You can calculate that, and recall and those things. This you can get from your scikit library, right? So if you use the scikit library or that classification report, right, you will get all the matrix, right? Then micro, so you can also get the macro F1 score values. Apart from this, for multi-class line cover segmentations, you can use these matrices like overall accuracy, total accuracy, average accuracy, all things, right? So this is, you can see that, confusion matrix for the multi-class, right, whenever get it, right? But for multi-class, apart from this overall accuracy, class-wise accuracy is very important. Class-wise kappa coefficient is very important. So you need to do the class-wise analysis as well, in addition to doing the average. Because what happens, average may be high, until and unless you see that, right, each class, what the class-wise their impact on that, right? So you see that maybe some may happen, some class is most dominated, right? Some class may be that poorly performing. If it is poorly performing, there is a problem. Algorithm is not good, right? Or your data set is not good, right? So you need to see that. Until unless you do the class-wise analysis, you don't have the crystal clear idea on your predicted results. So class-wise, that analysis is very important, right? That's also need to explore. So this is class-wise accuracy, which is called user accuracy basically also, right? So these things already been shared, you can go through that, right? Kappa coefficient is very important, right? So kappa coefficient, especially when you do the change analysis, you see that accuracy is high always, right? But kappa coefficient give you the crystal idea, right? Get complete idea which algorithm is good. Otherwise, all algorithms will be giving the better results, right? 99, 99, no. That's what will happen. So that's why this kappa is a balance. It also comes under accuracy parameter, but this is more balanced than the average accuracy, what you see that, okay. So this example will be, I'll stop that 2 minutes, right? You can see this PPT will be shared, right? So you can explore later on whatever is there. So this is my just lab, quick as my NITK lab. This is my lab, computer vision and deep learning, and here is this my team. So this is Rabia doing PhD currently. This is optical. This is Bibha. She is remote SAR data doing the research, and this recently graduated Basuraju, and this is JRF currently there in lab. So three mainly the 1 GRF and 2 PhD there in my lab. Soon going to be 0 because not getting the student nowadays very difficult. And this is my collaborator, research collaborator. So you see that ISRO very closely last many years. And first name is Professor Fabio, working many years, right, jointly. And apart from this, there are other my collaborators, this globally are there. These are the significant projects which related to the space. This project is going on. already done. Only the web-based development is pending. Will be completing by May. This project comes this year for again remote sensing from Karnataka government. These two projects I have completed already from this specific domain ISRO. This one and this for MIT. These are research areas quickly, and good quality publications we have contributed, journal 25 plus. So these are just output of my labs. Basically the DHAZI, we also work on that. The real optical data, fusion, despeckling, SAR despeckling, object segmentation, you have seen there these examples, right, which comes from my lab. This cloud segmentation, right, we have also done that. And this change analysis, we have as a part of ISRO project, we have done that. And you will surprise these are the BTech students. This work done by the BTech. Most of the innovations, right, in the beginning, right, last couple of years comes from the BTech. Whether in the remote sensing or the healthcare, BTech is the, what they do, all the foundation, all create everything. BTech creates and PhD will take it forward next level. That's how operating lab. This is another model, right? Fabio sir is there, right? In our paper as a UCDNet model, right? This change analysis, this conference paper we got published and got best paper also, SAR change analysis. These are the couple of publications, right, related to specific remote sensing. Thank you. Any questions I can take? Right. Anything, any doubt, any field even, deep learning in general also, not remote sensing. So in the lab session, right, you will be doing the code already will be shared. So as your task is just try to understand that, okay? Run that and try to execute, try to understand that. I hope maybe it will be difficult for some people, but fine, at least. And through your collab, how many of you already work on the collab? Raise your hand. Okay, perfect, right. So through collab, just try to execute, get some idea, right? And anyway, is there always with you, okay? So you can further explore, extend, collaborate, right now. So that will be helpful. Any assistant require, any help from my side, you can reach it through email, through even WhatsApp also. So both the things are available in my NIDK web page sites. And on recent update, you can check my web page. So like some more data set will be released, new paper will come. Of course, until we publish first, we cannot give data to anybody else. Because we are creators, so at least we want one good paper should come. Because then only you cite reference, no? Otherwise, question will be there. How this data set is, a good data set, right? Someone has to accept, no? Okay? Fine? Thank you. Thank you for listening. Anyway, I am there with the lab, okay? Tomorrow I will be talking mainly on the change analysis, right? From the SAR data.